path dotted with the force. Okay? And this gives us, of course, our change in energy. So if we take the bit inside here, we can call this an infinitesimal unit of energy, the path dotted with the force. And if this seems strange, go back to that lecture when we were talking about our full definition of work, and I talk about that a little bit during that lecture. So we know essentially that du is equal to ds dot f. So we're going to change this equation a little bit into force equals negative du dx. So this is for a one-dimensional system, and you think typically path opposing force, so we get rid of this dot product and put a negative there. Right? Also remember that in the full version of this equation, we have a plus or a minus depending on whether we're working against or for a force. So this is the typical version of the force potential energy equation, and it has a lot of applications even outside of gravity and stuff like that. I may talk about that a little bit later. Okay, so now we'll talk specifically about gravity. du equals negative f g dot dl. Okay, and if you want to know where this negative sign comes from, well, we're going back to this equation here, and we're taking the case of the negative sign because if we're firing a rocket or some other object, we're throwing it up in the air, we're doing work against a force, so we get a negative sign there. Okay. So, yeah, I have enough room, I think. This equals negative, and then we get another negative because the force of gravity also has a negative in it. Again, all these negative signs can be quite confusing, but usually you can just look at your final results and know whether you've done the negative sign correctly or not. So now I'm just plugging in our equation for gravity, dot dl. And I've made one of the masses the mass of the Earth because we're talking about escape velocity for the Earth. If we were doing some other planet, this would be some other mass. So after we take all those dot products and cancel out the negative signs, we have du equals g m r squared dr. Right? Only the radial distance is important because we have that dot product. So from our perspective, right, if the rocket isn't going straight up, if it's going, following some trajectory like this, like they do when they are sent into orbit, right, that distance it moves laterally for the escape velocity calculation isn't important because of that dot product, only the radial distance. So even if it goes like this, we still just take that radial distance. Okay. Obviously, if we want to do an exactly correct version of this calculation for an actual rocket, we would add in other complications like air resistance or the fact that it's using up fuel or etc. Right? Because fuel has mass, and therefore your mass changes as you go up. Okay. So now, in order to get the potential energy, we just integrate this equation. So u integral du equals integral dr g m over r squared. Okay? Which, just rewriting this in a simpler form, GMM integral dr r to negative 2. Okay, so we add 1 to the exponent, divide by the new exponent. So negative g mm over r plus u naught. Okay, this u naught comes from us doing an indefinite integral. Okay, and this is going to play an important role, which I'll talk about in just a second. So now we have our potential energy for a gravitational system where we have a radius large enough where the variation in the Earth's gravitational field as a function of distance matters. So when we're going so far up that we have to take into account that variation. So when we're putting things into orbit, we're talking about things that are already in orbits. We now have the energy equation that allows us to calculate the dynamics of that system, much like we talked about U equal simply mgh, and that allowed us to do problems when we were talking about things happening near the Earth's surface, like the ball rolling down the hill, or the thing drops the thing and pulls the other thing, and whatever else. Okay. So now, more complicated equation than mgh, but it allows us to do the same sorts of calculations we would have been able to do with mgh. Okay, so now I'm going to talk about this u naught there. So this equation is a little tricky to understand. I wish I had more board space. I'll do this. I'm just going to rewrite that at the top, and then I'll have more room to draw. So we have u equal negative g mm over r plus u naught. So let's graph this function. Okay. So this is u as a function of r. This is r. Okay. So this function looks like this. Okay. So this seems to make no sense because, well, if we follow this curve, this is the potential energy curve. As two objects get closer, they get negative infinity potential energy. What could that mean? And if I go really out far in r, as far away as I can get all the way out to infinity, my potential energy is just 0? Well, no. I still have this u naught there, okay? And in principle, I can choose any energy for u naught, and if I always keep that same u naught in whatever equation I'm using, then everything works out okay. Right? As long as I am consistent with my choice of u naught. The reason for this is that what's not important is absolute energies, but changes in energy. Right? So if this causes some change in energy, but both include this u naught, then the u naught, of course, is going to cancel out. Right? So the fact that we have this u naught that pops out is telling us that we have the freedom to choose whatever we want for our base level of energy, and all the dynamics still work out correctly because what's important is this variation, right? So if it made you feel better, right, you could say, okay, this is infinity, and then the lowest amount of potential energy then is 0, but then of course you have problems because then you have infinity plus 0 over here or whatever else. So point of fact, this is just chosen to be 0, and then we think about the maximum amount of gravitational potential energy we can have is also 0. Okay, that's a little bit weird to think about, but it's consistent, and it's mathematically simple and gives us all the correct answers, right? So in a gravitational system parameterized by this energy equation, the maximum amount of gravitational potential energy you can have is 0. And that's when an object is far out at infinity. Right? Why is this? Well, imagine there's only two objects in the universe, a large gravitating object and a smaller object, and I put that smaller object at infinity. Well, if there's no other forces in the universe, it's going to feel that force of that one infinitely distant thing pulling on it, and then I wait infinite time, and then that thing eventually building potential energy as it falls and falls and falls through infinity to the other object. By that time, it's built up itself an infinite amount of kinetic energy, right? So over here, right, at infinity, the object has 0 potential energy, and has 0, the maximum amount of potential energy, but also has no kinetic energy. And then it starts getting negative values of potential energy, but now the kinetic energy gets positive, right? Kinetic energy is still defined positively, and then I get more and more and more as I fall down. Okay, so when we're doing calculations, you might worry, well, how do I deal with these infinities? Well, thankfully, physical objects get in the way, right? If we have the Earth, well, the object can't fall past the radius of the Earth. Eventually, that object falls and it hits the surface of the Earth. Whatever happens to it, happens to it. And then I never get down to this infinity because there's stuff in the way. And even if you might think, well, if I drilled a hole straight through the Earth, then I could get to that point. Well, the only matter that affects an object gravitationally is the matter that's below it, right? If I were to draw something like this, right, and I won't prove this, but it's something that can be proven fairly straightforwardly. I believe it's in the book. But, so I drill this hole through the Earth, right? The matter that gravitationally affects me is only that matter which is where I am, or less than that, right, below me, essentially, in this spherical shell. So as I go from here to here, all of this matter stops affecting me gravitationally, and that's because, well, it cancels out, right? If I'm here and I'm worried about a lump of matter over here affecting me, well, I also have one over here, and one over here, and one over here, and one over here. And it's just the geometry of this that all of those vectors cancel out. So I'm only left with the ones that are inside. Okay, that's a bit of a conceptual and perhaps confusing explanation. But the point is that as I fall through the Earth's surface, less and less of the matter in the Earth affects me gravitationally until I get to this center point. And at that center point, all of the matter is pulling on me exactly equally, right, if everything's spherically symmetric. So I feel no gravity here, right? There's no gravitational potential energy in the center of the Earth. So as I get down to here, right, this goes back up to 0 essentially, right? Because there's less and less gravitational potential energy, right, that can affect, or less and less gravitational force that can affect me. Okay? So again, we've defined U as a function of R equals 0 as maximum energy. Okay. I'm going to go a little over time, but I just have one more page of notes, and it will hopefully be satisfying to finally do the calculation I've been talking about while I've been demonstrating all this, which is how do I find the escape velocity of a rocket? Okay. Or anything else that I want to fling into orbit. Okay. So, escape velocity is the amount of velocity an object has to have to escape the gravitational field of a planet. So on the Earth, it's the amount of velocity you would need to have to get up and far enough that the gravity of the Earth isn't really affecting you anymore. So in technical fact, this is at infinity, right? When we're far enough away from the Earth that we never feel its gravitational force anymore. Obviously that's a simplification, but it's a pretty good one because we have that inverse square. The farther out you go, we get to the point where, you know, the particles of space dust near you are influencing you more than the gravity of the Earth if we go out far enough. But technically we put that point at infinity, right, as a mathematical simplification. So if we fire an object from the Earth's surface, what does the velocity of that object have to be such that it can, in principle, get out to infinity, escape the Earth's gravitational field forever? Well, we have conservation of energy. Energy initial equal energy final. Right? That energy initial is going to be U plus K initial, and that of course is UF plus KF final. Okay? So we want the minimum amount of energy we need to escape the Earth. Right? So any extra energy can go into some additional velocity that thing still has once it's at infinity or just very far away from the Earth. But we want the minimum, so we're going to say that UF plus KF equals 0. So again, that UF being 0 is like saying, well, we have the thing at infinity, it's got the most gravitational potential energy we can give it, which by our previous definition was 0. So 0 is the most potential energy we can have in the configuration when the object is farthest away from the Earth. The fact that we're saying we want just enough for us to get there means that when we get there, we're going to have no kinetic energy left over. So UF plus KF, both 0. So together they're 0. Okay. So then we just have one side of the equation. The initial, let me write this the other way around. The initial gravitational energy is G, mass of the Earth, mass of the rocket, or projectile, or what have you, divided by radius of the Earth. Right? We don't have a square here because we're talking about energy, so that square went away when we took the integral. Plus the kinetic energy, 1/2 m escape velocity squared, equal to 0. Right, so we just take this guy, flip it over there, do some simple algebra. The mass of the projectile will cancel out, and we get escape velocity equal to 2g m Earth radius Earth. Okay. So if we plug in these numbers, we get escape velocity as 11.2 kilometers per second. So if I had a cannon that could fire a projectile at 11.2 kilometers a second, which is unbelievably fast, right? I could fire a projectile so far that it could entirely escape the Earth and go travel across the universe forever, essentially. Okay. Now, you might be saying, well, rockets don't travel that fast, because they can't, because we can't build anything that goes that fast. Well, rockets also are continuously applying thrust, right, and also losing a lot of their mass as they shed fuel, right? Most of a rocket is fuel. That's why bits fall off of it as it goes farther up, because it's dead weight now, those empty tanks and stuff. Also, we don't shoot rockets to infinity. We shoot them to orbit, typically, or to some other part of the solar system, right? So we're not going all the way to infinity. Okay. So this, of course, is a simplification, but it's just a several line calculation. Okay. All right, sorry for going about 5 or 6 minutes over. You should have had turned in your homework by now. Of course, I will be understanding if you'll have technical problems. We're all in difficult situations, and I understand that. Please go to the comment section and ask me any questions you may have. Have a great day. Bye-bye.